Hello and welcome to another math video. Today we'll be looking at the topic sets.
It's broken into two parts, and we'll be looking at the first part, which is set 1. We'll be looking at a number of subtopics, and they are 1. Finite and infinite sets, 2. Subsets and supersets, 3. Equality of sets, 4. The universal set, the unit set, and the empty sets. 5. We'll look at the cardinality of a set. So let's start by understanding the definition of sets. Sets are a collection of objects. They could be a collection of items. They could also be a collection of symbols. And let's not leave out letters and numbers. These collections are usually items that are of interest to us, and they are usually enclosed within braces and or brackets. These collections are also known as elements. Sets can be presented in any one of the following ways. They are 1. By a given rule, which are usually mathematical in nature. Consider a set A, which is given by the inequality x greater than or equal to 2 but strictly less than 10. Bearing in mind that x is an even number obeying that inequality. This means that the elements in this set will be 2, the next element will be 4, the next element will be 6. And the very last element in this set will be 8. Notice we do not include 10 in this set because the inequality says x will be strictly less than 10. Another way a set can be presented is by description. This simply means that we describe the elements we expect to see in the set. We can describe the set A as follows. A being even numbers starting with 2 but excluding 10. Moving forward, a set can also be presented by listing. This means we directly list out the elements, separating them with comma and enclosing them in brackets or braces. Using the same example of set A, we can list out the elements directly: 2, 4, 6, and 8. To perform any operation in sets, we must make sure that they are presented in the form of listing. So just a quick summary on what we've learned so far about sets. Sets can be presented in any one of the following ways. Number 1, by rule. Number 2, by description, which means we describe the elements that should be in the set. And lastly, sets can be presented by listing. This means the elements of the sets are written, separated by commas, and enclosed within brackets or braces. Next, we have type of sets, which will be the bulk of what we'll be discussing in this video. Number 1, finite sets. A set is finite when its elements are countable. There are examples that are showing up on your screen right now. In each example, it's observable that you can actually count the elements contained in the sets. Number 2, infinite sets. A set is said to be infinite when the elements are uncountable. We use dots to represent the infinite elements in a set. For example, let's consider the set n of natural numbers, which are indeed infinite in nature. So we have 1, 2, 3, 4, and the rest are in dots. Let's look at the set of negative integers. -1, -2, -3, -4, and so on. The same can be said for the positive even numbers, which are 2, 4, 6, 8, and so on. A null set is an empty set which contains no elements. Take note of the symbols below. A unit set. A unit set is a set that contains only one element. It is also called a singleton set. The following are examples of singleton sets, and in each example we can see that it contains only one element. Hope you're catching up. We still have lots to learn. Next, we look at supersets. A superset contains all the elements in another set and more. Consider sets A and B. What do we observe? It is obvious that the elements in B are already contained in A. Hence, A is a superset of the set B. In the next example, we can see that X is a superset of the set Y. This means Y is a subset of the set X. Can you think of another example? Do leave your answers in the comment section below, and let's get on with the video. Earlier, I made mention of subsets. The set A contains elements 2, 4, 6, 8. Let's look at the possible subsets. B, which is equal to 2, C is equal to 2 and 4, and D, which is 2, 4, and 6, and so on. Can you think of any other unique subset of A? Do leave your answers in the comment section below. I will be glad to reply your comments. Let's look at equivalent sets. The sets A and B are equivalent simply because they contain the same number of elements. Sets A and B contain 4 elements each. Sets R and S contain 5 elements each. Not necessarily the same elements, but the number of elements are the same. Comparing that with equal sets. Sets are equal if they contain precisely the same elements. Sets B and C contain the elements 2, 4, 6, and 8, though their arrangements differ. Similarly, F and G contain the elements 10, 20, 30, and 40. Sets of this nature are called equal sets. Can you think of sets that are equal? This draws us to the conclusion that equal sets are equivalent sets, but equivalent sets are not equal sets. A universal set contains all possible elements and subsets. The symbol for universal sets are U or E. If my interest is in letters, my universal set will be all the letters of the alphabet. And we know that there are 26 alphabets. That means this particular universal set is a finite set. Suppose my interest were to shift to the natural numbers. Then my universal set will pretty much be every number I can imagine. Such a universal set is infinite, meaning that the elements cannot be counted. If set A is a set of all positive even numbers and set B a set of all positive odd numbers, then we can see that the universal set governing set A and B will be the set of all natural numbers starting from 1 to infinity. Next, we'll look at the cardinality of a set. This refers to the number of elements contained in a set. The symbol for cardinality of a set A is n of A. Let's look at the following examples from 1 to 5. We want to determine the cardinality of each of these sets. Observe that example 4 is an empty set. The answers are as follows. Cardinality of A is 1, cardinality of B is 2, cardinality of X is 9, cardinality of Z, which is the empty set, is 1, while the cardinality of Y is 3. Please observe that for example 4, which is a null set, the cardinality is the empty set itself, which means it is 1. This leads us to the conclusion that every null set is indeed a unit set. Thank you for listening and see you in the next one.